Good morning. Today we will discuss multiple regression. Multiple regression. The contents of multiple regression are: first we will start with a conceptual model. Then we will describe the estimation of parameters. Then we will go for sampling estimation of parameters in terms of beta vector. Then sampling distribution of beta estimated. Then we will go for sampling distribution of error. Estimated. Then we will go for that model fitting issue, that is adequacy of a regression model. Then we go for test of individual regression parameters. Test of individual regression parameters, that is all betas. After that, we will test the assumptions related to regression. Then there are certain diagnostic issues. Then prediction using multiple linear regression. Finally, a case study will be shown. So, this is in totality will be covered under multiple regression. So, we will go by the first the model, then estimation of parameters, sampling distribution. I think today we will be able to cover this one, conceptual model and estimation of parameters. I think this is for 1 hour. Then sampling distribution of that beta estimates and sampling distribution of error estimate. I think 1 more hour is required there. Adequacy regression and this test of individual parameter may be 1 more hour. Test of assumption 1 hour. Then diagnostic issues 1 hour and prediction 1 hour and case study 1 hour. So, 1, 2, 3, 4, 5, 6, almost 6 hours we will be discussing on multiple regression. Now, let us start with an example. I think in first class and also in subsequent lectures, I have given one example for the CT-CAN data. CT-CAN is a small company working in the local market, and we have seen that the data structure was like this. Other way, we can start with the variables. The important variables for this particular company are profit, then sales volume, then they have found out the percentage absenteeism of workers or employees. Then related to machine, that machine breakdown hours monthly. Then they also have a marketing department whose performance is measured through M ratio. The company's primary interest is how to improve the profit, that definitely through maximizing the sales. And apart from many other things, the company is interested to know how these three variables, the absenteeism, breakdown hours and M ratio is affecting sales volume as well as affecting profit. If this is the case, then under this situation there are two types of variables, one called dependent variables or dependent variable DV, another set is known as independent variable which is IB, independent variables IVs. So, in this case profit is one dependent variable, sales volume is another dependent variable, and there are three independent variables like absenteeism, breakdown hours and M ratio. Now, what is of interest in this particular case? Here we want to test that whether the independent variables are contributing in explaining the dependent variable one at a time, dependent variable one at a time, it is happening or not. If we can find out that yes, there is influence of the independent variables on the dependent variable, then depending on the influence measure, some actions can be taken to control the dependent variable with the help of controlling the independent variables. So, pictorially, if we now consider that one dependent variable, let it is sales volume which is y, we are denoting like this, and other variables we are denoting like this, x1 equal to percentage absenteeism, x2 equal to breakdown hours, and x3 is M ratio. So, we are not considering profit at present, later on we will see that how profit also can be included. So, under this situation, if I define like this, that y within a circle or ellipse and x1 within a rectangle, x2 with another rectangle, x3 with another rectangle, and I can create some straight line with curved with the arrowhead to y, then this will determine that the respected IVs are influencing the dependent variable y, that is the measure. So, that means x1 influences y, that is why the arrowhead emanates from x1 and terminates at y, that is the case. Okay. So, we can say that if x1 has influence of beta 1, x2 has influence of beta 2 and x3 has influence of beta 3. What does it mean? It means that if I change 1 unit of x1, there will be beta 1 unit of change in x2. If you change 1 unit of x2, there will be beta 2 unit change in y, and if you change 1 unit of x3, there will be beta 3 change in y. Repeating, if you change 1 unit of x1, there will be beta 1 unit change in y. Similarly, if you change 1 unit in x2, there will be beta 2 units change in y. 1 unit change in x3 causes beta 3 units changes in y. Okay, this is the meaning of these influencing parameters. Now, what will happen, suppose none of them, for example, absenteeism, breakdown and M ratio, none of them contributes to y. Will there not be your sales? Is it, there will be sales also. It is not necessarily that they have to contribute always. So, in that case, we require some other parameter which is known as beta 0, that is coming through x 0, where x 0 takes value of 1, that is always, okay, x 0 equal to 1 always. By saying this, what we are trying to say, that even if there is no influence of x 1, x 2, x 3, still there will be some amount of y values. This is the constant term beta 0 is added there. Now, if you take one observation of y followed by second, third like this, what will happen? You will find out that you are not able to explain using beta 1, beta 2, beta 3 and beta 0 and all these values, not able to explain the total variability in y. That means, there are some other variables or some other, either they are controllable or uncontrollable variables are there, which are also contributing towards the variability of y. So, as a result, what we require? We require another measure which is known as error. That means, in multiple regression case, you will get three types of, I can say, parameters. One is beta 0 constant parameters, which is known as intercept. Then the influence of the independent variables, these are known as that influencing parameters or regression coefficients. Also beta 0 is also regression coefficient, intercept coefficient. Then another one is a random one, which is error, which also contributes. So, essentially then what will happen, if I want to put the entirety in terms of an equation, I can write like this: y equal to beta 0 x 0 plus beta 1 x 1 plus beta 2 x 2 plus beta 3 x 3 plus epsilon. You can very well write this one. So, that means this figure is the pictorial representation of multiple regression model, which in mathematical term you can write using an equation. Okay. Now, as we have said that x 0 will take value of 1 always. So, this can be written like this: beta 0, beta 1 x 1, beta 2 x 2, beta 3 x 3 plus epsilon. Okay. Now, if we generalize this one, that we are not interested only in 3 variables, we will go for a variable vector which is having what I can say p variables, let it be. So, I am writing like this: x 1, x 2 dot 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 x p. So, there are p variables which are contributing towards y. Okay. And as we have already seen, there is one intercept parameter, and with related to one constant x 0, that one we are making it 1. So, we can write, if we want to create this x in terms of, also we want to add x bar x 0, then you can write this one p plus 1 into 1. See, this x 0 is it is not required to be written here, later on it will be taken care of. Essentially, this x 1 to x p is the variables IVs, x 0 is a constant, that intercept term will come for that. Okay. So, okay, then if we go by x 1 to x p, this is p cross 1 variable vector. Under this situation, what will be the beta? Because there will be influence for each of the variables. So, I can write beta 1, beta 2 dot 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 beta p, which is p cross 1. But see, there is one intercept parameter related to x 0. So, that is beta 0. So, you require to estimate p plus 1 parameters, regression coefficients here. Okay. Now, I can write now like this: y equal to beta 0, beta 1 x 1, beta 2 x 2 dot beta p x p plus epsilon. So, this is in general the general regression equation. Okay. This is the general regression equation. You can write later on we will write it in terms of matrix equation. Okay. Now, let us assume that you are collecting data. So, let n data points are collected. Or you can are collected or to be collected. If you say to be collected, this will be all observations will be random. So, in this case, so our data matrix will be, first one is the dependent case. So, y it will be y1, y2, y3 like your yn, n data points. Then you are collecting x, that will be n cross p. N is the number of observation, p is the number of variables. So, we will use here x11, x12, x1p, x21, x22, x2p. So, like this xn1, xn2 dot xnp. Correct. So, this is related to IVs, these two sets of data you will correct. Now, if you use this data set into the equation given here, so for every data set or every data points, this equation will become true. So, in order to incorporate that every data points into consideration, if I write one yi here and then here it will be xi1, xi2 like xip. This is what we are saying the general observation related to this. Now, if we want to write the equation here, then what we will write? We will write yi equal to beta 0, beta 1 x i1 plus beta 2 x i2 plus beta p x ip plus epsilon I. Getting me? Then what is this quantity? This quantity you see, it is a weighted linear combination of several variables. Here basically multiple random observations. So, can we not write down this is variate? This is linear combination, weighted linear combination, this is variate. Then what does this variate represent? In this case, this one represent the expected value of yi given xi. What is this? Xi equal to basically xi1, xi2 like this xip. Getting me? Without error term, this one is the expected value of yi. If I know the ith observation for the individual variable IVs, then what will be the expected value, what will be the value of yi, that is the predicted value. As we do not know that what are these IVs for the ith observations, so accordingly we also do not know what will be the yi value, but by this variate we are basically saying that what will be the expected value of yi if you collect ith observation xi1 to xip. Okay. And then that means what is happening, then yi equal to this plus epsilon I. So, this one, this expected value is nothing but the predicted value. Okay, suppose you want to use this later on, this will be the predicted value. So, I can write from here that epsilon I equal to yi minus yi cap. So, essentially what are the things we have found out here? We have found out all the coefficients, regression coefficients, also the error term. Also that, and we also describe that that this linear combination of this is the variate, and this variate will basically talks about what will be the value of expected value of y given this condition. So, it is a conditional y. We also write this one that mu of y given x in general term, we will write mu of y given x. If I say yi, then given xi, where xi is, this is the xi observation. Okay. Why so? If we further assume little bit, this is because you just assume that there is one x and one y, and you are fitting a linear line. Suppose this is your xi, and so what will be if this is the regression line, the linear line, then you go like this, you will be meeting, you are getting this point here. What is this value? This value here, this is nothing but this value mu, mean value of y for the ith observation, given ith observation. Now, why we are talking about mean value? The reason is, suppose you collect for the ith observation, if you collect one now, you will get some value here. If you collect tomorrow, the value may change. So, ultimately there will be one error part. So, this one is taken care of by the concept error. So, any point on this regression line which you will be fitting later on, these points are the mean value of y given x. Okay. So, we will see later on when we will fit all those things, I will tell you that how to make all those things. Okay. Now, we have collected n data points, and we have also our regression equation that yi equal to beta 0 plus beta 1 x I1, beta 2 x I2, like this beta p x IP plus epsilon I. If I write it for all the observation, then y1 will be beta 0 plus beta 1 x 11, beta 2 x 12, like this beta p x 1p plus epsilon 1. For y2 you will be writing like this beta 0 plus beta 1 x 21, beta 2 x 22 plus beta p x 2p plus epsilon 2. If you go on writing, ultimately up to the nth term, you will be writing like this beta 0, beta 1 x n1, beta 2 x n2, beta p x np plus epsilon n. So, if I write in matrix form now, can I not write y1, y2 like yi, then yn for the left hand side? You can write this. So, this is n cross 1 vector. I can write this equal to, if here for beta 0 there is only 1, that x 0. So, 1 1 1, for beta 1 x, what is this, 1 1, x 2 1, x I 1, x n 1, for beta 2 x 1 2, x 2 2, x I 2, x n 2. Similarly, for beta p x 1 p, x 2 p, then x I p, then x n p. Fine. So, this one is now what will happen here, there are n into p plus 1, p variables, 1 for the intercept. So, if I multiply it by beta 0, beta 1 to beta p, this will be p plus 1 into 1. Then the multiplication of this will give you n cross 1. It is giving you n cross 1. So, n cross 1 equal to n cross 1, which is basically this portion is taken care of by this, plus there is error terms epsilon 1, epsilon 2, epsilon I, epsilon n. This is n cross 1. Okay. So, the resultant can be written like this, y equal to x beta plus epsilon. Okay. So, where y is n cross 1 vector of observations of the dependent variables, x, this is n into p plus 1, the data matrix of IVs including intercepts. This is also known as data matrix. Actually, x is this one including intercept. So, we say this one is design matrix, correct. Beta is the p plus 1 cross 1 regression coefficients, and epsilon, this is n cross 1 error terms. N cross 1 error terms. Fine. So, this is in nutshell equation for multiple linear regression in matrix form. Okay. Now, we will see some of the assumptions of multiple regressions. First assumption is linearity. So, that is linear relationships. Second assumption is homoscedasticity. Or we say equal y variance across the values of x, otherwise you can say IVs, different observations of IVs, that homoscedasticity. I will show you for how it will be done.
Equal y
Variance across y, across x, y variability remain constant. Then third one is, we have seen that the error term is there. So, the error will be uncorrelated error terms. That means there are n into cross 1 errors, this vector, this will not be correlated, uncorrelated error terms, and definitely linearity normality of the error terms, normality of the error. So, these 4 assumptions need to be tested later on. After fitting the model we will test this, but at present, at this moment I should say something about what is this. So, first understand what is linearity. You consider your relationships y versus x. For example, it is x1. Then when you plot the data, so if you plot the data, so suppose you are getting this type of relationship. When you are plotting with x2, you may be getting this type of relationship. So, in the first case there is linearity, in the second case it is a non-linear one. So, if your data that y versus x, that relationship is non-linear, then this model is not applicable. What you require to do then? You have to convert this to linearity. You have to transform the data. Primarily we want that you transform IV, first case, from linearity point of view, you transform it, so the data becomes linear, the relationship becomes linear. Now, your relationships can be negative, positive, no problem, but linearity is a issue. Second one is your homoscedasticity. I told you just few minutes back that suppose this is my x, this is y, let it be, because as 2 dimensional 1 x. Your regression equation, let it be like this. We are assuming that one fitting is possible, linear fitting is possible. So, you have collected data points, n data points, suppose this is x1, this one is x2, and then you will go for this one is xi. So, similarly last one, let it be xn. So, what I said that this observation, this is the first observation, I equal to 1, this is I equal to 2. So, like this I equal to n. We are saying that you will collect one sample, but you may collect several samples also. So, under such condition what you will get, for a particular value of x, you may get several values of y. So, if you plot this, several y values for a particular value of x, then whatever variability of y you observe, that must be equal. So, that means we are saying this one, if it is sigma square, suppose y equal to 1, so y 1, sigma y 2 square, sigma y 3 square, sigma y n square, I think this is I square. So, what is the condition? Sigma y 1 means at x equal to 1, this y 2 y I y n square, this should be sigma square. This is what is homogeneity from variability of y point of view. If there is violation of this, for example, your plot may not be like this, your plot something this, here it is okay, but here maybe it is like this, here may be again small, here may be against big. So, across x values y is not homogeneous from variability point of view. That assumption if violated, you require to transform variables, but in that case you have to transform the y variable. If there is a linearity problem, you transform the variables, you can go for both, but it is preferable that you transform the x variable. If heterogeneous nature, that heteroscedasticity is there, that means not equal variance is satisfied. So, that in that case you have to transform the y variable. Okay. Then third one is uncorrelated error terms. Actually, you see this equation, this figure. So, when you use regression equation and you predict, you will basically predict these points. For x equal to 1 this value, x equal to 2 this value, 3 I this value, so n this value. Getting me? So, the remaining portion is the error. Suppose your case is like this, your original value is here yi, then you are based on this equation you are saying this is yi cap. So, this portion is my error portion, this is the error. So, similarly everywhere you will be getting error. Error what will happen? Here it is sigma epsilon 1, epsilon 2, epsilon I, epsilon and error. Uncorrelated error terms, because each error is random now. So, the error will follow this type of distribution. Epsilon I will follow normal distribution with mean 0, and what will be the variance? Variance will be sigma square sigma y square. That means what is this one? Sigma y square, we are writing it is a sigma square equal to sigma y 1 square equal to sigma y 2 square for all observation for equal variance. So, this condition is very important because we are considering this variability part will be taken care by the error. So, error will follow normality with mean 0 and variance sigma square, where the sigma square is the basically the y variability for each of the observation of x. Now, what we are trying to say further, that suppose there are two observation error terms yi and yk, then the covariance between these two will be 0, that is uncorrelated error terms. So, as there are n errors, so if I see the covariance matrix between the error terms, what will be the n cross n matrix you will be getting? Diagonal elements will be the variance of diagonal elements should be 0. That is what uncorrelated error terms. And normality of the error is this, error will follow normal distribution with sigma square, variability mean 0. So, these are the assumptions. We will test all those assumptions later on when we feed regression equation and it is required to be tested. Okay. So, once you are satisfied with the data, that examining the data you find out that okay, that assumptions are reasonably valid, then you will go for fitting, that is estimation, modeling or estimation of parameters, estimation of model parameters, that is beta. We are talking about how to estimate the beta, where y is x beta plus epsilon. This is my MLR. This is my MLR. So, if you recall that we say yi is beta 0 plus beta 1 x I 1 beta 2 x I 2. So, like this beta p x I p plus epsilon I, and if we do little modification here, then this will be y I minus sum total of j equal to 0 to p beta j x I j. When j equal to 0, this x I j will take the value of 1. So, if I make a square of it, then you will be getting y I minus j equal to 0 to p beta j x I j square. Okay. So, this is for a particular observation, but we have n observation. So, if I take summation over n, what is this quantity? Sum square error, sum of square errors. So, this one is SSE. Now, we will choose beta j values in such a manner that SSE will be minimum. So, your ultimate optimization issue is here, choose beta in such a manner that SEC is the minimum. Okay. So, you can do very easily this one. So, we can write SSE also in some other way also. What will happen? You have to go for derivation SSE by del beta j, this you put equal to 0. Subject to what? Subject to that your del square SSE by del beta j del beta k, this is greater, because it is a minimum case. So, we basically now what happened? We are here also I am saying that only for one variable case beta j, here it is 2 beta k also we have taken, that means the covariance part is that 2 variables this is coming into. Actually what is happening here, there are so many variables, p variables.
Sir, here should be means del square SSE divided by del beta j beta k or only d2 square.
You are talking about when there is only one variable, we say this by, now if k equal to j, it will take care of that issue. It is general form we have written basically.
Then basically the Hessian matrix.
Hessian matrix. So, actually that I am trying to say, as there are p plus 1 estimates you are making, so you will be getting a matrix. So, Hessian matrix, that matrix will be positive definite, will be positive definite. That is what I mean to say, that is why I have written like this. Okay. So, every component you will be calculated and a matrix will be found, and that matrix will be positive definite. By positive definite we mean that suppose A is a square matrix. Now, you get any vector in x, if you find out that x transpose x greater than 0, that means A is positive definite. Okay. So, what the Hessian matrix will come, that must be positive definite, then it is the minimum condition. Okay. So, now let us write in terms of matrix, then we found out that epsilon is epsilon 1, epsilon 2, epsilon n, that is n cross 1. We are making SSE means square, some square error. Can we not write like this? This is a vector. So, 1 cross n, n cross 1, this will give you 1 cross 1 scalar quantity. If this is true, can we not write like this, y minus x beta transpose y minus x beta? We can write, because our y regression equation is this. So, epsilon is y minus x beta, you can write like this. Now, if I take derivatives against beta, then you will be deriving this one, it is nothing but the square term. So, ultimately what will happen, it will come like this, 2 x transpose y minus x beta. 1 x transpose will come from here, then derivative this will remain this, because we are deriving the derivatives for beta, and one will come from here, and this with matrix compatibility you will get this equation. So, this equation will put to 0. So, I can write now that minus x transpose y plus x transpose x beta equal to 0. So, I can write x transpose x beta equal to x transpose y. If I multiplied both side by inverse of x transpose x, then what will happen? What I have done? I x transpose x inverse I multiplied both side. Now, x transpose x inverse x transpose x, in the covariance lecture I have given you that SSCP matrix x transpose x. Can you remember that data covariance time? And I say that this is basically square matrix, symmetric matrix. So, the inverse times this will be identity matrix.
Sir, as generally it is full rank, that's why.
That's why full rank case. So, this one is identity matrix. So, I can say that beta, we are writing now beta cap, because we have taken the x transposes all these fixed values which are collected from the sample. So, this will become x transpose x inverse x transpose y. Okay, so, this is your formula for estimating regression coefficients. Getting me? I will show you one example for the estimation part. Let us solve this one problem. Suppose y is 10, 20, 30, 40, 50. This is my 5 cross 1 vector, and my design matrix is 1 1 1 1 1, that will always be there. Then let it be, it is 5 7, then 10, then 12, then 20. We are taking, it is basically 5 cross 2. So, that means only one variable, independent variable we have taken, that is x, and this one is your x 0, only one you have taken. Okay. So, what you require to calculate? You require to calculate beta cap, which is x transpose x inverse x transpose y. So, you first find out, your step 1 is find out x transpose x. So, that will be your 1 1 1 1 1, 5 7, 10, 12, 20, this is x transpose. Then your again x transpose x only. So, 1 1 1 1 1, then 5 7, 10, 12, 20. Now, this matrix become 2 cross 5, this is 5 cross 2, the resultant will be 2 cross 2 matrix. So, you will get this x transpose x, if you 1 into 1 like this. So, there are 5 data points. So, you will be getting 5 first, this into this like this. Now, this into this like this, sum of this 5 plus 7, the 12, 22, 34, 54. Other side also this cross this, that also will become 54. Now, 5 into this 25 plus 49 plus 100 plus 144 plus 400. So, 9 plus 5 14 plus 4 18, then 4 plus 4 8 plus 2 10 plus 1 1, 4 4 okay 10, then 4 plus 1 7. So, 7 1 8. correct. So you second what you require to compute inverse. So I say this is my step 1. Now step 2, I want x inverse x transpose x inverse. So this is my determinant of x transpose x, that 1 by this adjoint of x transpose x. So determinant of x transpose x equal to determinant of 5, 54, 54, 718, which is 5 into 718 minus 54 square. This will become 5 into 8, how much it is? 40 plus this 9, 35090 minus this quantity will become 16962916, and the resultant quantity will be 674. Okay. Now adjoint of this matrix 5, 54, 54, 718, this will become, so 718 will come minus 54 minus 54 5, this will be like this. So your x transpose x inverse then will become 1 by 674 into 718 minus 54 minus 54 5, this will become, the quantity will become something like this. If we go by this by this will be 1.07 minus 0.08 minus 0.08, then 0.007. If you go little, and if you want to make it, then 01 something will come for digit case. Okay. Then what you require to know now? You require to know x transpose y. That is another thing you have to compute. Then your step 3 is compute x transpose y. So this one can be written like x transpose y is 1 1 1 1 1 5 7 10 12 20. This is my 2 cross 5 into 5 cross 1, the 10 20 30 40 and 50. So this is 5 cross 1. So it will be 2 cross 1. Resultant will be 2 cross 1. So now the 10 all will be summed here, 10 30 60 150 finally. Then this is 50 plus 140 plus 300 plus 480 plus 1000. Okay. I think this quantity will become 0 this side, this 5 plus 4 9 plus 8 7, then 4 plus 3 plus 1 8 plus 1 9, this is 1970. Okay. So your step 4 is beta cap equal to x transpose x inverse x transpose y. What is our x transpose x inverse? We found out x transpose x inverse, I think. Yes, x transpose x inverse is 1.07 minus 0.0801 0.0801 0.007 into x transpose y is 150 1970. So this quantity will be, this is 2 cross 2 2 cross 1, it will be 2 cross 1. This into this minus this into this, the quantity will become like this: 160.50 minus 157.80, and it will become 2.70. Similarly, other one will become minus 12.015 minus 13.79. The resultant quantity will be 1.775. Okay. If this is the case, so my regression equation is now y equal to beta 0 plus beta 1 x1 plus epsilon equal to 2.70 plus 1.775 x1 plus epsilon. This is your regression equation, and your y cap will be 2.70 plus 1.775 x1. This is y cap. And if you want to find out the epsilon cap, the error term, that is y minus y cap, which is y minus y cap, you have to find out. So now this one, you have y values, like 10, 20, 30, 40, 50, and you require to find out y cap. How do you find out? You have x values also. X values are 1, 1, 1, 1, 1, then 5, 7, 10, 12, 20. Okay. So it is 2.70 plus 1.775. What is x1 value? 5. 2.70 plus 1.775 x2 value 7. 2.70 plus 1.775 x3 value 10. 2.70 plus 1.775 12. 2.70 plus 1.775 into 20. This will give you your error values. It will be 5 cross 1. Okay. I think this is what is estimation. We have calculated very simple problem, only one variable at a time. So when you take y is function of f(x) in the linear mode like beta 0 plus beta 1 x1 plus epsilon, only one variable, this regression is known as simple regression. Simple linear regression, when that means p equal to 1 case. P equal to, now if it is p is number of parameter to be estimated, then it is 2, intercept plus this. And if I say p is the number of variable case, this is only 1. So when it is p greater than equal to 3 or more number of parameters to be estimated, or other way I can write p plus 1, if should be 2, then it is simple regression. When p plus 1 greater than equal to 3, that will be multiple regression. Okay. But all those cases y is a single dv, y is our single dv. Okay. Only one dv at a time we are considering. So next class we will see the sampling distribution of beta. Now beta you have estimated, this beta cap, I am saying sampling distribution of beta cap, that estimate basically. So this beta cap you have estimated using a sample. If you go for several sample, the beta cap value will change and it will become it is a random variable. What about beta? Is it a random variable, the beta, the regression coefficient from population point of view? You have y equal to x beta plus epsilon, which we are talking about. It is our regression line for the population. Beta is the population parameter. So that constant, and it is unknown. So that's why you are obtaining this beta cap, which is estimate of beta, and expected value of beta cap will be beta. This is the unbiased estimation. Fine. So, beta is constant and random, constant and unknown, constant and unknown, and beta cap is random variable, but it is known now. When you are collecting data, you are getting this value. So, we will go for sampling distribution of beta cap. Okay. Next class.